All right, we have now started the second phase of the topics in this course. Up until the previous video, we completed various ways and methodologies of generating samples from a particular distribution. Now, what we'll do now is we'll learn a little bit about what can one do once we've generated samples from distributions and how they might be a bit important in various fields of engineering and physics, etc. We might not get into a lot of real life examples, but certainly we'll look at the computing tools that are needed within those. So most of what we'll talk about in the next sort of 3 to 4 videos will be motivated by the idea of simple Monte Carlo. Okay. And again, we've learned many ways of sampling from different distributions. And what we'll do is now we'll implement these in this process called the simple Monte Carlo process. So suppose small f is some distribution. This is suppose capital F is some distribution with density small f. Okay, so we'll be quite careful about what are distributions and what are densities. Capital F will denote the distribution function of a particular random variable, and small f will denote its density function. We are going to be limiting ourselves mostly to continuous random variable, so we can very well talk about density functions instead. Okay. Now we are interested in estimating the expectation of some function h, which is mapped from the support of my density up to R. Okay, so for clarity, I have that this is my support of F. So this is the whole. This is where my target density F takes positive values, and I map H to R. Let's say so. It could be any function. Now, what I might be interested in is in estimating theta, where theta is nothing but the expectation of H under, oops, there's another typo, sorry about that, under F, right? Or, sorry, capital F. So I want to estimate expectation of H under the distribution capital F, which means I am interested in estimating the integral h of x times small f of x dx, means h of x times the density function with respect to which I'm actually trying to find the integral or the expectation. And I assume that this quantity, this mean of h under f is finite. So if this is a little confusing, think of h of x as just being the identity function, in which case theta is nothing but the expectation of x under my target distribution f. Now, what I want to warn you against a little bit is that I am not at all talking about data here. Okay, this is not a problem that involves data currently. There is no data here. There is just an integral. Okay, there is an integral that can look like an expectation, and I want to solve or solve or obtain an answer for what that integral might look like. Okay. But and this integral might be annoying. It might not be solvable using all those very interesting integral solving techniques that we know. There might not be a nice closed form solution to what the integral turns out to be. So the integral might be annoying, and we are interested in estimating this annoying integral. Okay. Now, this notation again means that we're taking the expectation with respect to f, and from now on, and particularly while we are talking about Monte Carlo and important sampling, we want to really focus and understand on the distribution with respect to which we are taking an expectation. Okay, so we'll be very cognizant of that in all the topics that we'll be doing. Okay, now this is the integral I want to estimate, and this is nothing but the mean of h under f. Right? Now suppose I have a mechanism with which I can draw samples x1 up to xn, IID from f. Okay? Suppose there's a mechanism using which I can draw x1 up to xn in a way that's independent and identically distributed from f. Okay? And again, this we can do using probably the many methods that we've already learned. Let's say f is the normal distribution, or the gamma distribution, or exponential, or Cauchy, um, or maybe even chi-squared. We have learned methods of sampling from various distributions. And let's say I get IID samples from this distribution. Then, in order to estimate theta, which remember is just the expectation of h under f, I can use the sample average of h of x to estimate the population average, right? This is the population average. And I can use theta hat, which is the sample average, to estimate this population average, okay? And that's exactly what the simple Monte Carlo estimator is. So this is basically the simple Monte Carlo estimator. And it might be weird to think about why this has a special name if it's just the sample mean or the average. And the only reason this has a special name is because the samples from which this is generated or this is calculated are not real data. They're actually simulated on a computer. Okay, so there is a mechanism through which we can generate samples, and then we just take sample averages of appropriate quantities. But then further, by the law of large numbers, okay, we know that as n tends to infinity, theta hat converges to theta in probability. Okay, so as we get more and more samples, theta hat gets increasingly closer to theta. Further, we can also find the variance of the estimator, the variance of theta hat under the distribution f. So here f denotes that the samples that are involved in theta hat are coming from f. Now variance of theta hat is nothing but variance of 1 by n summation t going from 1 to n h of xt. But then I can pull this 1 over n outside and I get 1 over n squared, summation t going from 1 to n, variance of f of h of xt, right? And here I've also taken the summation outside. And I can take the summation outside because all of the xt's are independent. Because they're independent, the variance of the sum of independent random variables is the sum of the variance of the individual independent random variables. Okay. But now what I note is all of the hxt's are exactly distributed similarly. So as random variables, they have the same variance, which means this sum I can write as n times variance of maybe just the first one, okay, divided by n squared. And once I do that, I can cancel one of those n's out with the denominator and I just get variance of h of x1, which now I denote as sigma squared by n, which means I have essentially said that sigma squared is nothing but variance under f of h of x1. Okay, so we have that our estimator converges to our quantity of interest theta as n tends to infinity, and we have a sort of expression of the variance of the estimator as well. Okay, this is the idea of simple Monte Carlo. Okay, and we have other tools. Now, naturally, a central limit theorem will also hold because our theta hat is nothing but a sample average. Because it's a sample average of IID random variables, I can employ this central limit theorem exactly and immediately, assuming this is finite, where this was, remember, nothing but sigma squared. So if sigma squared is finite, then as n tends to infinity, square root n theta hat minus theta converges to normal 0 sigma square as n tends to infinity. Okay, and then we can use this a CLT to make inference or to understand variability or to make some confidence intervals around theta hat for theta. Okay, the idea is that as statisticians or people involved in data science, we are not happy with just a point estimate of theta. estimating theta is not enough. We also want to understand what is the variability associated with that estimator. Is it a good estimator? Is it a bad estimator? Does it work well? And the variance and the distributional behavior of the estimator helps us understand that. Okay. Now, this was nothing but simple Monte Carlo. But then a natural question to ask is there a way that we can obtain a potentially better estimator of theta? We've done this, we've obtained samples from F, we've taken a sample average, but can we in some way construct a better estimate of our integral of interest? And the answer to that is possibly, not always, but possibly by using the idea of importance sampling. Okay, so in this video and in the next few videos, we'll continue talking about various aspects of importance sampling. Okay, so what is importance sampling? So first we're going to talk about simple importance sampling, which is, and then we'll do something called weighted importance sampling. But remember, in our original goal remains the same, is we want to estimate an integral theta, where theta is, over script x of h of x, f of x, dx. This is our theta, right? And this is what I want to estimate. Okay, now, and recall h is such that it's a function from my support till r. And again, this is what I want to estimate. Now, what we'll do in importance sampling is similar to the accept-reject algorithm or accept-reject sampling methodology. We will choose a proposal distribution via some ideas. Now, how exactly will we choose them? I'll get to in a later video. But this means that let G, okay, capital G, be a distribution with a density G. Now here again, I'm differentiating between distributions and densities. Okay, so let G be a distribution with an associated density G that is potentially defined on script X. Okay, and it's defined on script X, which is to say script X, recall, is the support of F, right? So G is defined on script X so that I can write S expectation of H under F as just this integral. That's not confusing, hopefully. But then what I do is I do something smart, is I recognize that over script X, on this support, G of X is greater than 0 on script X, which means that I can divide by G of X because it cannot take a value 0. Okay, and that's important. So it can't take a value 0. So I divide by Gx. Okay, and because I'm dividing, I'm also multiplying so that I've made no changes. Okay, now once I've done this, what I notice is that, look, this thing is a function of x, h of x, f of x by g of x, and this is integral of this quantity with respect to g of x dx. Right? Which means this is nothing but the expectation of h of z, f of z by g of z, this function, with respect to this, the distribution corresponding to this density, which is g. So I can write expectation of f of h as exactly the expectation of hf by g with respect to g, where this z again is from g. Okay? Right? So again, I can write the same theta, which was this, as this quantity over here, which is again, I can write as this quantity over here. And this is true for all appropriate g's. So as long as this holds true, we can do this, right? As long as I'm not dividing by 0, we can certainly do this. Okay? So now how do I use this relationship? Now there's no statistics happening here really, because there's no data yet, all right? There's no random samples that I've obtained. But as soon as I've written this theta as this expectation, I have an alternative estimator. If I get multiple samples from G and take a sample average of this quantity, that will also estimate theta. And that's exactly what the importance sampling estimator is you get Z1 up to Zn, IID from G. Okay, so independent and identically distributed from my proposal or importance distribution G. Then an estimator of theta is theta hat g, which is 1 by n, summation t going from 1 to n, h of zt, f of zt by g of zt. Okay? So again, I get my samples from G and then I take a sample average. All right? That is my importance sampling estimator. The estimator theta hat G is the importance sampling estimator, and the method is called importance sampling, and G is called the importance distribution. I will often also call this or just the proposal distribution, the importance proposal. So what is actually going on in this situation? So let me denote Wt as f of zt by g of zt. So for any zt that's from g, I can calculate this quantity over here, which I will call as the weight associated with z of t. Okay. Then using this, I can write the same importance sampling estimator as 1 over n t going from 1 to n. Oops, not f. H of zt, W of zt. So what this says is actually this is nothing but a weighted average, right? This is nothing but a weighted average of the H of Z's. Right? But weighted by what? That's the question, right? It's a weighted average by Z, but weighted by the weights F by G. So the weights associated is the density function of the target distribution at Z and density divided by density function of the proposal distribution. Okay. Now, intuitively, this means that depending on how likely a sampled value is for F and G, a weight is being assigned. What this means is if I sample G from an area of high probability under G, then this will be a large value. And if that sample value is also under an area of high probability for F, then this will be also a large value. Okay, so overall, this might be a value maybe close to 1, not too large, not too small. But if I sample a value that's in an area of low probability for G, okay, then this denominator is small. And if it's in a high probability of F, then the numerator is large. Okay, and then that means these two together makes the weight really large. Okay? So in the plot over here, this is exactly what I do. Okay, so there's a small typo here. So this is exactly what I do. So over here, I'm drawing a target distribution, which is in this black curve over here. So this target distribution, in black, I have f of x, okay, and in red, I have my g of x, my importance proposal, okay, and in blue, I have my weight z of t, which is equal to f of zt divided by g of zt. Okay, so basically, if I look at, let's say, this point over here, okay, then for this point, my target density, for this point, my proposal density takes a relatively larger value than my target density. So this ratio over here is going to be less than 1. And so the weight is fairly small at this value, right? The height of the blue pillar. Versus, let's say, over here, okay, my proposal density takes a very small value, but my target density takes a really large value. So this value is really large relative to the proposal density value. And so the weight assigned is really massive. It's like a massive weight that's assigned. Okay. So one by one, I will generate these ZTs from G, right? So I will generate from this red curve. And I will generate these values less. So whenever I generate them, values here, I want to give them a large weight because they are really good values under the target. Okay. And when I generate values here, which are really good values under the proposal, but not such great values under my target, then I don't want to generate them. I don't want to give them a lot of weight. Right? And that is the idea behind importance sampling is it's a weighted average of the edges, weights depending on how likely are the values themselves under the two different distributions being contested. Okay. So this is sort of an introduction to simple Monte Carlo and then importance sampling. And then in the next video, I want to go over a few examples regarding this as well.